Hey everyone, this video is about interpreting data from a titration curve where you are looking at the pH of a solution versus the volume of titrant that you've added during the titration. This is exactly the kind of data that you're going to be collecting in lab this week. All right, so this titration curve is for a monoprotic acid, HA. So monoprotic meaning there is one acidic proton on this acid. The acids that you'll be titrating in lab this week have two acidic protons. They are diprotic acids. And so your data will look somewhat different. You'll get to explore that in lab. All right, so the reaction we're doing here, you can see that as we add titrant, our pH is increasing. And since it's increasing, as we add something, we know that what we're adding is a base. So the reaction that we're doing here in this titration is our weak acid HA reacts with the hydroxide anion, giving us the conjugate base of our weak acid plus water. Okay. And so here at the beginning of the titration curve, we have almost entirely HA. A little bit of this weak acid has dissociated. And we could use our equilibrium constant Ka to figure out just how much. And then as we start adding base, here in the middle, we have a combination of HA and its conjugate base A minus. Right? And so here in the middle, where we have both HA and A minus present, this is the buffer region. And then eventually we run out of HA and we stop being able to buffer the addition of OH minus, and pH starts to increase much more rapidly. And then here, this is the end point of our titration. And here we have essentially just A minus. Right? Both at the beginning and end of the titration, there is a little bit of reequilibration that happens. You have small amounts of A minus here, very small amounts of HA here, and small amounts of A minus here, but not enough to meaningfully shift things. Okay. And so all through this buffer region, we have a very useful equation that describes the relationship between pH and the amount of HA and A minus that we have in our system. And that's the Henderson-Hasselbalch equation. And it is that pH is equal to the pKa of your acid plus the logarithm concentration of A minus divided by the concentration of HA. And the way you remember the order here, your mnemonic is that this spells aha when you look at that fraction. Right. And so one of the useful things that comes out of this equation is the fact that when you have equal amounts of A minus and HA, right, so if you're exactly halfway through your titration here, right, you've turned half of your HA into A minus equals HA, and so A minus divided by HA, since these two numbers are the same, this equals 1. And if you take the logarithm of 1, that's equal to 0. 10 to the 0th power is 1. And so that means that when you are halfway through your titration and A minus equals HA, this term of the Henderson-Hasselbalch equation is equal to 0. And pH is equal to the pKa of your acid. And so just from looking at one of these titration curves, if you can find your endpoint, which you can find by finding where pH starts to increase rapidly after a region of being relatively flat as you add titrant, right? Halfway between your starting point and that endpoint, the pH in your flask is going to be equal to the pKa of your weak acid. And so here we can see that the pKa of this acid is a little bit above 4. So if we go ahead and we try to estimate this, this is about 5, halfway from 4 to 6. Here's 5.5. So I'm going to go ahead and call this pKa 4.3. Right, so just from looking at this data, we can estimate that pKa of this weak acid is about 4.3. And this is the approach that you'll be able to use with your diprotic acids. Your titration curves will look different, but you'll be able to use them to find pKa's, and you'll be able to use the endpoints to calculate molecular weights. And all of that information together can be used to identify the weak acid unknown that you've been given. All right, we will see you in lab this week.